All right. And are there like some lightning tricks that you've learned so far by working, like for example with the ray tracing, some ray marching, or anything?
Um, I would say temporal supersample anti-aliasing is very nice. Temporal reprojection is very nice. Well, whatever project you start or begin working on, you should definitely get that in because there's just a whole bunch of things where you can just say, oh, we just make this stochastic and temporal reprojection is gonna fix it. Or you can basically say, um, we're gonna reduce the quality and that temporal reprojection is gonna fix it.
And
Uh,
what's the temporal projection doing exactly? Like, why is that fixing stuff?
uh, Basically, what it does, um, you keep a cache of a previous frame. You might just keep the previous frame. You might keep the previous resolved frame, which is basically the already filtered frame, or you might keep a cache of previous frames which are unfiltered. Nowadays, we mostly do it with already filtered frames because of the bandwidth and the memory constraints, and also that if you keep a previous frame, it kind of has like this geometric average behavior, where basically you slowly blend um, all of the previous frames together, as except for last n frames if you keep them unfiltered. But basically, what temporal reprojection does, it reprojects the current pixels into previous frames locations and looks them up in the previous image, and then tries to use the information from the previous image to improve the quality of the current image. Which makes a lot of sense because um, I've even thought about this when I was 14. I was like, why are we like, if something doesn't move in a frame, why are we drawing it every frame, right? So like when you've got like a city landscape and maybe only some characters move or something like that, why every frame do we redraw the city, right? So what temporal reprojection anti-aliasing does is basically it doesn't stop you from doing the extra work, but at least it improves the quality. So by applying a jitter, or just basically by the virtue of the camera moving a little bit, you can blend previous pixels together, which helps with the aliased edges. It helps with specular aliasing, for example, when you've got really shiny surfaces. If you want a real nice example of a game where you can see specular aliasing, you should play Metro 2033 and Metro Last Light. Even the Redux editions have specular aliasing, mostly because back in those days they didn't really do a lot of research into how to filter the mip maps of a specular texture in the normal map, of a roughness texture in the normal map. But yeah, basically, temporal anti-aliasing would help with that. It will help you with um, um, it might even help you with stuff like screen space ambient occlusion. So normally, what you do is to get the ambient occlusion, you'd do a few samples around the pixel, kind of estimate how occluded it is from the positions of the other pixels around it. But the thing is, you can't do it. You can't check every single pixel around it because that would just take too long. So what you do is basically you have a sampling pattern which is kind of random, and the pixels they have gaps between them. You don't check every single pixel, and because of those gaps, there's a lot of noise. It's because sometimes you might miss a feature, but in the next pixel over, it might actually hit that feature. So you've got the grainy noise. And what has been the technique for ever since screen space ambient occlusion was used in games, which was 2007, 2008, up until 2016 or even 18, is basically we're going to take this noisy image, which we have computed at half scale anyway, or maybe even quarter scale. And what we're going to do is we're going to blur it, but in a way that doesn't cross any edges. And then we're going to upscale it, bilinear upscale, which is like a clever upscale where you basically take an average of the four surrounding pixels, but try and not use the pixels which you know that are on a different surface. So that's the way that was always done. So obviously this screen space ambient occlusion doesn't get you any of the really tiny features, and it's it's not very sharp. It's very kind of like washed out. So what you can do instead is you can actually do the screen space ambient occlusion at full resolution with even less samples, and obviously get horrible noise. But because the temporal anti-aliasing reprojects, an infinity of frames behind, or maybe on average 16 or something like that, and you've got the jitter pattern, then what happens is that when you resolve that, you can get an image which looks like you've used 16 times as many ambient occlusion samples. So you can basically save on the bilinear upscale and on the blur filter, which was supposed to remove the noise from the ambient occlusion. And that's really powerful. Temporal anti-aliasing is basically like a very primitive denoiser. For ray tracing, we've got other things which work a lot better. But temporal anti-aliasing is very simple, and you can leverage that not only for ambient occlusion, but you can also leverage that even for lighting. If you, for example, decided to evaluate the light for every 16th pixel, and then over the course of 16 frames, you changed which of the 16 pixels it's going to be. So if over 16 frames, if you didn't move the camera, you would have eventually calculated the light for every single pixel, and you boost the light by a factor of 16, then what temporal anti-aliasing would do, or a denoiser, was basically blend all of those 16 frames, backwards in time after reprojection, and you'd pretty much get the same result as if you were always doing the light calculations for all of the pixels, not every 16. That's really powerful, because what it enables you to do is either have the lighting portion of your game take 16 times less time, or you can have 16 times as many lights, or maybe 16 times as big a resolution for the same cost. And the only reason we don't do that right now in games is because shadow mapping is still popular. That would be a lot of wasted effort to basically to do the shadow map without any gaps, only then to stochastically evaluate the lighting. But it's something that we do with a ray tracer on a daily basis. If you have a ray tracer, you don't actually evaluate all the lights. You pick a certain number at random out of how many lights you have, and then basically either keep on doing that until you get a reasonably converged result, or apply denoisers and temporal reprojection.